So, welcome to my talk about Lua. You might know me from the meetup, but these are also the various places that you can find me online. And today we will be talking a little bit about Lua. So a quick show of hands, who of you has worked with Lua before? Just, oh yeah, that's quite a lot of hands, okay. Let's maybe start a little bit of history. So what is the first thing that comes to your mind when you think of Lua? Like, just shout it out. What's the first thing that people associate with the language?
Pre-make.
Pre-make, okay, that's a good one. Maybe another one?
Testing.
Minecraft is very close. So games is actually one.
Embeddable.
Embeddable, yeah, that's also good. But I was actually going for games because most people that when they think of Lua, they think of it. It's a scripting language that's very popular in games, right?
And that association is Redis.
True. Yeah. Yeah. Why is it that Lua is so popular with games? So who remembers this? Which game is that? Shout it out. Which game?
Monkey Island.
Exactly, Monkey Island. So it's The Secret of Monkey Island, to be exact, which was the very first Monkey Island game released in 1990. And I'm not sure if you can read it, but you probably know because, come on, you're Germans, you've played this. This is called the scum bar. Scum bar, so SCUMM. So this is obviously not the English word scum, because then you wouldn't need the second M. So what does scum stand for? What is this an abbreviation for? Does anybody know? So it's the scripting system, exactly. So scum is a scripting utility for Maniac Mansion. And it's the scripting language that was invented by Ron Gilbert at his time at Lucasfilm Games. And it has actually been used as the scripting language in every 2D Lucasfilm and LucasArts adventure game. So this is like sort of a tribute to the programming language that drives it all underneath. So why am I telling you this? What does this have to do with Lua? Well, as I said, scum has been used as the language in every 2D adventure game. When they actually, like the big 3D boom hit in computer games, and LucasArts decided, hey, our next point-and-click adventure game is going to be 3D, they actually noticed that scum doesn't work very well with 3D. So they basically, if they had to adapt it to 3D, that would basically have been a complete rewrite. The people at LucasArts at that point said, okay, like, let's just take a look at what is out there already in the world before we go ahead and again invent our own scripting language. Maybe in the meantime something has come up that solves our problems. And this was around 1996, 97, and curiously, Lua at that point was pretty much unknown in the Western world. It had been developed at a university in Rio de Janeiro, in Brazil, and due to political reasons, it was very hard at the time, during the early 90s in Brazil, to use software that was not developed in Brazil. There was like some embargoes on it, and it was very hard to get stuff imported. So they created this scripting language to solve like the problems that they had at the time. But since it happened pretty much without anybody from the outside noticing, basically no one outside of Brazil knew it. Until they published an article in Dr. Dobbs' journal in 1996. That was when journals still came in paper form, where they sort of presented the language to the world. And it just so happened that Brad Moglevsky, who was the lead programmer on LucasArts' first 3D adventure game at the time, Grim Fandango, read this article and decided, hey, that sounds pretty cool. And he got into contact with the Lua guys, and then they decided to adopt it. as their new scripting language for the 3D games. And if you look at the first Monkey Island in 3D, they actually have a Lua bar in there now. So this was basically how it all started. Like after Grim Fandango was released, Brett gave a talk at GDC where he again talked how they adopted Lua into the game engine, and that was basically the real beginning of the success story. Nowadays you can find Lua in lots of different applications. One of the most famous examples is probably still World of Warcraft, which uses it as the scripting language for the user interface. So World of Warcraft is actually extensible by the player through an API that allows them to write UI customizations. Then we see in the upper right corner Adobe Lightroom, which is software that is written to, I think, a little bit over 60% in Lua code. Then we have Love, which is basically a 2D game engine that is scriptable through Lua. It's very popular for game jams and like smallish games by people who are just starting to learn games and like don't know programming well enough to start with something like C++. And Lua is also quite popular in the embedded world. So what we see here is the Node MCU, which is an Arduino-based chip that is quite popular in the maker community. It comes with a Wi-Fi chip, so it's a chip that is very well suited for small IoT-like maker projects. So what is the one thing that Lua does really well and does better than others? Lua is small, and by that I not only mean that the binary is small. It is like the compiled binary is less than 180K on Linux, and that actually includes the full standard library. You can make this significantly smaller by stripping out the library and the parser if you only need to execute bytecode but don't need to compile yourself the scripts. But Lua is also small in terms of language features. So what you see on the left, you're not supposed to be able to read it. It's actually the complete syntax of the Lua language in EBNF form, and it nicely fits on a single sheet of A4 paper. The complete reference manual is 82 pages, and that actually includes all the standard library functions and the complete C API. There's only 8 basic data types in the language, so you can see from these numbers, if you compare this to a scripting language like Python, where the philosophy is like batteries included, you get like a whole bunch of stuff and everything you could ever ask for. Lua is pretty much the opposite of that. It's like as small as you can make it while still keeping it useful. And the interesting thing is that for the Lua people, this is not, they don't really see this as a limitation, they rather see it as a virtue. And I hope I can give you some examples for why this is the case. So one consequence of Lua being small is that the whole language fits into your head. And this, I think, is a really big advantage that should not be underestimated. Like with C++, if you're programming it, you never have the whole thing in your head. Like you constantly need to swap in and out like different parts of the language depending on what you're doing. So you need virtual memory up here to make that work, right? With Lua, it all fits in the cache, right? You can all keep it up here. So yeah, as I said, with other languages, this is really hard, especially with C++. There's no way that you can do it unless maybe you're one of those guys. Okay, one short disclaimer before we're getting started. This talk has the problem that I cannot assume that you already know Lua too well, but I also want to give you examples that are somewhat interesting. So if at some point you think that the examples are overly contrived or maybe a little bit too complex, and you think, oh no, this is not a language that I would want to work in, please blame that on the talk and the examples and not on the language. With that out of the way, this is Hello World. Two things here. My syntax highlighter likes to make the print blue. That does not mean that it's a keyword. It's just a standard library function. It's a function like any other. The other comment, the semicolons in Lua are optional. You can write them, but you don't have to write them. And when I was writing to the Lua mailing list to get feedback on the talk, that actually spawned like a little flame war on the mailing list. So, like, yeah, don't start discussing about that. Like, you can go on for ages. So I usually write the semicolons here because, like, you C++ developers, right? You like your semicolons. Okay, so one thing that is special in Weis, so this is just a function declaration, simple enough. But in Lua, actually all functions are lambdas. So what does that mean? It means that this declaration that looks somewhat familiar is just syntactic sugar for what we have down here. So we create an anonymous function value, and then we assign that to the variable of the name f. Right? So f is just a variable like any other, and we just assign to it a value of type function. And this is already one thing where we notice the smallness of Lua. Like they don't waste like some special syntax on like declaring functions. They just say like, we already have a feature for naming things through variables, so we just reuse that for functions, and then just make functions values like any others, like numbers or strings or whatever. There was a question.
In Lua, you can also put the strings in single quotation marks, no?
I think you can, yeah. So the question was if you can also put the strings in Lua in single quotation marks, and I think you can. Another question?
Can you reassign the functions?
Can you reassign the functions? Indeed you can. Yeah, functions are true first-class values in Lua, and we'll see what that means. So let's say we want to replace our print function because we don't like it, right? Then we can just do it, right? Just assign a new function, and we can do that with any function. Like standard library functions are not special. So, for example, let's say we want to count the number of print calls, like how many times did the enclosing program actually invoke print. We can do it like this. We just define like two variables, and then we replace the original print function with one that just increments the count and then calls the old print function inside. Yes?
How do you avoid like name collision? Because now you call it old print, but like how do you actually call the old print?
How do I avoid the name collisions? That's an excellent point. Because, as you might notice, I did not declare any variables in this program. And for those of you who have worked with scripting languages before, you probably know this. In most scripting languages, you can just use variables without declaring them. And it will just create a new global variable whenever you do this. Which is not so nice, right? Because like this could be dangerous, and we will get to that later. But first, let's talk a little bit about closures. So a big problem with this code is, of course, that the count and the old print, they now pollute my global scope, right? So count is not a name that I want to have in the global scope because I will get name clashes all over the place. So it would be nicer if we could move that to a more local scope. And in Lua, we can do that with by moving the variables as local variables into a function. So now I actually declared the variable, and I declared them as local. That's actually the only form of variable declaration that is allowed in Lua, and that restricts the lifetime of the variable to the function scope. I mean, just as local variables in C or C++. And now, what I can do, I can still refer to them in this way from within that function, and Lua will just implicitly capture the variables and put them inside the closure. So in C++, if you would do this, you would have to write the names of the variables inside the array brackets, capture them explicitly. Lua does this implicitly. But now we have a new problem, right? Because our account, the thing that we're interested in ultimately is now a local variable. So how do we access this value of the count again? How can we get it back? Well, but then I will have the original problem again if I put it in the global variable, right? So no, I just return a function that gives me back the count. So now whoever calls enable counting just catches this function. I think I don't have an example. Just catches the return value and then can call this function whenever they need to get the count back. And this might be somewhat surprising, right? Because if you wanted to write this in C++, that is not so easy, because the count is a number, and the number has value semantics. And it also has value semantics in Lua. This is not something that goes straight to the heap. And still, we are able to share the count between these two closures, and modify it and still have it outlive the original function in which it was declared. This is not trivial to implement. Nowadays there are like lots of scripting languages that can do it, but this is not a small feature. Like this is not a feature that you would necessarily expect in a language as small as Lua. But they had this very early on, actually before most other languages. Please, a question.
Would you be a web counting or?
Okay, so how is it implemented? Basically, the function keeps track of the closures that reference this variable, and then when the variable falls out of scope, it checks if any closures are still referring to it, and if so, the variable gets moved to the heap. And the closure, whenever it refers to the variable, it refers to it indirectly, so it's able to point either to the stack or to the heap, depending on where the variable is currently located at.
I'm sorry, can you compare it somehow to Python decorators? Or?
Can we compare it to Python decorators? You would have to ask a Python person for that. This is a Lua talk, sorry. Maybe. So one important consequence of this feature is that whenever you read function, you should read them as closure construction. So constructing whenever the control flow passes over the function keyword, that potentially has to construct a closure which captures state. So this might go out to the heap. This might generate some work for the garbage collector later. Okay, on to tables. Tables are the most important data structure in Lua. Almost everything in Lua is a table. So as we can see here, this is the simplest case. We construct an empty table. But what else can we do with it? So a table is an associative array. That means it's basically like an array. We can use it just like an array in C. But we can also use it as a key value map, as a dictionary. So as you can see here, here we use a string as key for indexing the table. But Lua does not stop there. In Lua, actually, any value can be a key. So you can use functions as keys, and you can also use other tables as keys. Please.
How does it know that it's a string that you use as the key?
How does it know that this is a string? We will see that on the next slide. I think like 2 slides more. But let me just reiterate that this is very much the Lua philosophy. Like when they provide a feature, they try to make it as general as possible. As we've seen before with the fact that functions are just values like any other values. A table is just a key value store, and it can map arbitrary values to arbitrary other values regardless of their type. So it just tries to keep things as open as possible, and that's where a lot of its power comes from. Tables also have reference semantics. So as we can see here, this is actually a way to construct a singly linked list in Lua. We just create 2 list nodes, and then we link them together through the next field. This basically works as you would expect a list to work. Note that you barely need to do this in Lua. Usually just using tables straightforward is good enough, but there are some seldom cases where you might want to build something like this. Again, similar to the function, whenever the control flow passes over the curly braces, that means a new table will get constructed, which means you just did something that the garbage collector will have to clean up later. Okay, so we already had the point about the strings somewhat being special in there. If you write a line like the one above, all of the keys that you specify here are interpreted as string keys. There's also a slightly more convoluted syntax if you want to use different values here, but if you write it like this, the keys are always strings. That means the second line, that is the natural way of indexing this, right? This is just the lookup into the table with the string as a key. But Lua also allows as a syntactic sugar the third line. So the second and the third line are completely equivalent. Whenever you use the dot, that basically means take whatever I write next as a string key for the table lookup. And this is actually how Lua implements records. So as you can see, this is a syntax that is very similar to accessing struct members in C, for example, and this is how Lua implements this. They just use the table feature that is already available for this. So now we have fields. All that's missing basically is member functions, right? So let's say I have my complex number here. Now I want to add a member function that takes my complex number and mutates it into its complex conjugate. Which I can do like this. Again, tables have reference semantics, so this mutates the table that I pass in as a parameter. And now turning that into a member function basically means I just assign the function to a field in the complex number table, and then I can call it like the line below. And if you're familiar with how object orientation is often done in C APIs, this is pretty much what they do. It's like passing this pointer explicitly to the function call. What is of course a bit ugly here is that we now repeat the name of the table. Like we have complex twice, once on the right and once on the very left. And that's why Lua offers some convenient syntax sugar here as well. The colon syntax actually is just syntax sugar for this passing this pointer that we see above. Okay, so now we don't really have types, right? So whenever we want to create a complex number, we basically call a constructor function like the one that we see here that stamps out tables that look like what we would expect from a complex number, right? So, like this. And now, of course, since we can now build a complex number, maybe we would want to add them with a convenient syntax like that one, which means we would like to have operator overloading. And in Lua, operator overloading is provided through a feature called metatables. So metatables basically mean I assign to a value a special table, and there are some of the fields in that table have a predefined meaning that tells the Lua VM how to interpret that type. So in this case, I can just define an underscore add function, which is one of these predefined special fields. And that will, given two complex numbers, return a new complex number, which is the sum of the two that I passed in. And now I can just change my constructor function to assign this meta table to all of the values that I stamp out and give out. And now I have operator overloading. Notice that metatables can actually be applied to all values, not just tables. So for example, one thing that the Lua VM does by default is it actually assigns to all string values a metatable that allows you to call functions from the string standard library as if they were member functions of the string. Also, metatables are extensible. Apart from these few predefined functions, you can also add your own non-standard fields if that makes sense for your application. And there's a question.
How would you make it possible that you can add two complex numbers or complex number and a normal number, a float or whatever?
How would I make it possible to add not two complex numbers, but a complex number and a normal number? Additionally. So the thing is that this would have to be handled inside the add function. So the function that I assign here, it can inspect its parameters and then determine like what their type is, and then go into a different execution path depending on what happens. The thing is, if you, I'm actually not sure what the exact rules are, like whether the left side or the right side determines which metatable gets used. So you might run into some trouble there getting that work nicely. So it works best with in the symmetric case. Yeah, please.
These special functions like add and so on, do they maintain then operator precedence?
Do these special functions maintain operator precedence? Yes, they do. The rules for how the operators get evaluated are not changed, just the underlying implementation that gives the result back. Okay. So let's talk quickly about encapsulation. So the problem that we have now with our approach of building records is that all of our members are just fields in an associative array, so they are public, right? Everybody can see them. And that is not always desirable. Sometimes we want to hide data away from the user. Like, let's say, for example, we want to build a date type where there's like complex invariance between the different fields, and we don't want the user to mess this up. So what we can do here is that instead of returning a table that has the fields for year, month, and day, we just return a table that has setter and getter functions. And here I just wrote the day, but you can also add functions for the other two fields. And now the actual data, so we assert the precondition, and then we store the actual data inside a local table. Again, a local variable to the function. But this is not a table that we give out. And then we do a trick similar to what we did before with the counter. For the getter and the setter, we just refer to this local table, which is then captured inside the closure of the getter and setter functions that we give out as part of the table. And then we can assert that our precondition is not invalidated when we set the day to a different value. And notice that we actually did not need any new keywords for that. We did not need any public, private, whatever. This comes just naturally from how tables work and how functions work, and you can build your own encapsulation if you want. So again, an example for Lua being small, right? They don't introduce a new feature, they just make the few features that they have powerful enough that you can build whatever you want. Okay, one of the nice things that all types are tables is that reflection is somewhat trivial. So if we want to check if a certain value is a complex number, we can just inspect if it has the right fields in the table set. Yeah.
Does it actually do a string comparison, or is it like smart?
This is, so c.real means you take real as a string and you use that string as the key for the table lookup.
I mean type C equals table.
This is type returns the type as a string. So this is really a string comparison.
Like a runtime string comparison.
Yes, but strings are like a runtime string comparison, yes, but runtime string comparisons are cheap in Lua because Lua uses pooled strings, so this is a linear time, a constant time thing. Yeah. So you can also do something like this. Here we use the generic for loop, which again is a loop that can do many things, and here we use it together with the pairs member function, the pairs function from the standard library. And what that basically does is it iterates over all the fields in the table and then gives us back the key and the value. and that way we can like trivially convert a table into a tuple. Okay, so with that, we like given a table in our hand, we can like reason about what it looks like. But what about global variables? Like, how do we know which values are like floating around in our program? And in Lua, global variables are actually just entries in a table called _g. So assigning a global variable is just syntactic sugar for creating a new entry in this table, which means we get reflection. But that also means we can do stuff like this. So back to our function hooking example from before, we can now actually write a function that allows us to enable this counting functionality for arbitrary functions. So we just give the function name as a string argument to this enabler function, and then it just gets the original function from the _g table. And then it basically just plays out the same trick as before for getting the counting place. And getting back to a question that we had in the very beginning, we noticed that the fact that in Lua you do not have to declare variables is potentially dangerous. So for example, here I made a really stupid typo where I wrote a foobar instead of foobar, which means the interpreter will now silently generate a new value with the wrong type, and I might not notice this until much later in the program. So this is undesirable. But since the creation of this new global variable foobar is just the creation of a new entry in the _g table, I can use a metatable to make this illegal. So this _new index, this describes whatever happens if I use the array bracket operator, or like in general, if I create a new entry in the table, and here I just say no, you can't do that. And Lua actually provides an official module that does something a little more complicated like this, and the idea here is basically that you restrict the points in your program where you are allowed to declare new global variables. So for example, you can say you are only allowed to declare global variables in certain contexts, or you could say that you're only allowed to declare global variables if you go through a declare function that bypasses the metatable. Okay, that was actually the part about Lua. I'm a little bit behind time, but are there any questions about the Lua part so far?
Can you go back 3 slides or so?
Can I go back 3 slides? You say stop.
Stop. One.
This one?
What the hash? Is it
Oh yeah, the hash. Yeah, I will explain that. That actually gives you back the size of the table. Yeah. So here I basically built an array of all the values that were in the original table, and they're all like at the array indices 1, 2, 3, and so on. That's basically the idea here.
And you're dropping the keys.
Am I what?
And you're dropping the keys.
I'm dropping the keys. Exactly. I'm not using I'm not interested in the keys in this example. I could even use the underscore up there instead of the K to drop the value altogether.
Shouldn't it be hash coupled without the +1?
Shouldn't it? No, because in Lua indices start at 1. And this is because Lua was developed to be used by non-programmers, actually. And for people which are not programmers and have been indoctrinated with this notion of arrays starting at 0, this is actually not that unintuitive. So, you can also, I mean, the table is just an associative array, right? So no one will stop you from starting indexing at 0. But all these standard library functions and also like this length operator, they all assume that if you use the table in an array-like fashion, that the first array index is 1. So, yeah.
Is there a module to be used by programmers? I mean, like
Is there?
based index. No,
What?
just a joke.
Can you repeat the joke for the camera?
Yeah. Is there a module to so that Lua can be used by programmers?
A module to allow you to know. I'm afraid you would have to patch the VM to get that. Yeah, it's only non-programmers module. But you can get used to this. It's not that hard.
Yeah, but I'm not sure whether I can adopt back to C++.
Oh yeah. Like going back to C++ after this might be hard. That is true. Okay. Speaking about which, we have to go back, right? We have to integrate it with our C++ program. So how do we do this? As we've quickly mentioned already, Lua is an embedded language, so the main function still belongs to C++. And Lua is pretty much used like a library inside there. Before we can do anything with the Lua API, we have to create such a Lua state object, which in the end, of course, has to be freed already. And this is given as the first parameter to almost any API call. And once we have that, we can just execute some Lua code. So it's really as simple as that. If we want to expose C or C++ functions to Lua, we actually have to wrap them in a function that has exactly this signature. So it returns an indent takes the Lua status parameter. And as you might notice, there's no C++ parameters that are being passed here, so what is going on? And the reason for this is that the Lua API has this notion of a stack. This is not the call stack, it's slightly different. And all of the values that you want to pass into the VM or get out of the VM have to go through the stack. So if you have a value in C and you want to get it into Lua, you first have to put it on the stack, and then you can say, okay, now this stack value, assign it to like this global variable inside the Lua VM. So Fortran, yeah, so this seems like a very low-level approach. So why do they do this? Two reasons. The first reason is that it keeps the API small. We only have 8 data types in Lua, so we need 16 functions overall, like one for getting it on the stack, one for getting it off the stack, and that's it. That's all we need for getting values in or out of Lua. The second reason is a bit more subtle. It actually solves the ownership problem. In garbage-collected languages, there's always the problem. If I reference a value that lives inside the VM from the outside, I have to somehow make sure that the garbage collector does not delete this value from under me, and I'm left with a dangling reference. And since in Lua I can never reference values directly, but I can also only reference values that are lying on the stack, and the stack has strong ownership on the values, that actually solves this problem. So for those of you who ever had to integrate a scripting language into an enclosing C++ program, this can be a major pain, and I think Lua solved it quite elegantly by introducing this concept of the stack here. So yeah, let's put some values on the stack. I just used strings and numbers here as examples. The other values might be a little bit more complicated, but not much. So I have API functions for pushing them, and I wrap them in my custom push function, so I have now 2 overloads of push. And then I can define a variadic function that just takes a number of arguments and just pushes them one after the other on the stack. In case you're not familiar with this syntax down here, this is actually a fold expression on the comma operator. This is a C++ feature that was introduced in C++ 17. Basically that means like just invoke push for each of the different arguments that are passed in. And in C++ 17, they even guarantee that this maintains order if someone overloaded the comma operator, which was not guaranteed before. So this will never reorder your arguments now. Okay, if you don't have C++ 17 yet, you can also use a library to do the same thing. This shows how you could do it with Boost HANA. And if for some reason you also cannot do that, you also can write this monstrosity to do it in C++ 11. Please don't try this at home unless you absolutely have to.
Or use initializer list.
Or use initializer list. I'm not sure that makes it better. Okay, so that allows us to get functions into the VM. Now we just need to be able to get functions out of the VM. Since Lua is a dynamically typed language, this is the one point where we just have to do a switch case. But once we are through this one switch case, we actually want to return like strong types again, like a number type and a string type, so that we are in the nice, strongly typed C++ world again. But now, of course, the question is, what is the return value from this function going to be? So, yeah, but like number and strings are unrelated types, maybe. So, like we could define a base class, right? But nobody, like base classes are so 1990s. Nobody wants to do this anymore. So we just define like these two unrelated wrapper classes, but they might share like some common interface. In this case, like each value at least should be able to tell me its type. And then we can use a variant. Since there's only 8 data types total, and we know all 8 of them beforehand, variant is actually a pretty good match here. And you can even implement this quite efficiently in terms of space. So there will be some small space overhead for the primitive types, like number or bool, but it pretty much works out. You don't waste anything for the more complex types. So this is not a bad choice here. And then, yeah, we can of course use visitation to allow getting the type of a value like this. Okay, now we actually have everything that we need to call a Lua function from C++. First, we get the function by its name and put it on the Lua stack. Then we push all of the arguments to that function on the stack. Then we call the function. And then we have to inspect the Lua stack to get the return values back. So the way that this works is just, since Lua allows an arbitrary number of return values, we actually have to really look at the stack and then figure out through some API calls how many values are there and get them out of there. But that's really not too difficult. And then we can, like, for example, call the print function like this and like have it print the two arguments, a number and a string, like this. So as you might have noticed, this is sort of the most generic form that I can give such a function signature. It just takes like any argument type, and it just returns like any number of values of any type. If I know a little bit more about this function beforehand, I can constrain it further. For example, if I already know the number of arguments, I can restrict it like this. And if I also already know the types of the arguments, I might want to do something like this. So as always in C++, stronger types are better. So if you already have this knowledge, then you might want to go with the stronger types. Okay, like this is great. You can easily interface with Lua if you want, but let's say you want a little bit more convenience. There's a lot of binding libraries out there. I'm just going to show you some code from one of them, which is called Sol2. It's a single header only library, so you just pull it in like this. Instead of the Lua state, it actually uses its own root object, which is the Sol state. You can either use this as a state view, which is the non-owning version of this thing. But this is particularly useful if the rest of the application already uses the raw Lua API and you only want to use Sol in certain places. But there's also an owning version of this if you just use Sol for everything. And then, yeah, you can get basically you can basically wrap a function type inside C++ like this, and then just call it like we see down here. So this is basically saying we get the global variable print, and we bind that to a Sol function value, and then we can just call on that in the line below. Note that Sol is very eager on doing lots of implicit conversions for you. If print, for example, would not be a function, but actually like some other type, then this might lead to a runtime error. Having types checked really rigorously here is a bit more difficult, but it's also possible. let's now say, for example, I have a C++ function like this, which takes a number of arguments. One of them can actually be like any type. The v can just be any kind of type. And I also have multiple return values, which in Sol means I return the tuple. Then I basically don't have to do anything. I can just assign it to a sum func value in Lua like this, and that's basically all I need to do. I can just call it from Lua then, and the framework will figure out all the rest. And then of course I can also go full circle now. I can basically like go have a C++ call that goes through Lua and then again calls the C++ function that I bound before, and then the result travels all the way back. And here I use the structured binding syntax from C++ 17 to break up the tuple into the 3 individual values. Okay, so wrapping up. Lua is a powerful, efficient, lightweight, embeddable scripting language. This is the elevator pitch that you can find on Lua's homepage, like how they present their language in one sentence. I hope I could give you at least an idea now what each of these adjectives is supposed to mean in the context of Lua. I also prepared some references for you. The reference manual is actually really good. Like you can learn Lua pretty well from just reading that. But probably the best way of learning it is still the programming in Lua book. It's a relatively thin book, like roughly 300 pages, and a really good way to get started. Also describes a lot of language idioms, and it's actually also a good way to support the creators of Lua financially. As we mentioned in the beginning, it's still a university project. It's mainly maintained by 3 people. And in Brazil, it's not that easy to get funding, so I think they would be thankful for everyone who buys their book. And that's basically it. That's the end of my talk. If you have any questions, please state them now. Yes?
You presented this Sol library,
Yeah.
and there was a function construct where we can just load some function from Lua.
So you're basically talking about this Sol function. Yeah.
Is it possible to like load this function and then override it from C++, for example? Saying like, okay, now I want to load the print function in C++ and make it do something what I want.
You want to overload the print function from C++?
Override, not overload. I mean,
So
let's say I
do you
have
just
a
want to reassign the print function to a different value?
yeah, but implement it in C++.
Yeah, that's basically this line here. So you could just assign some func to print, and that's it.
No, I would use then SV print and then assign some function which I implemented in C++. So let's say I have a module in Lua where some functions are not so efficient.
Yeah.
I work with this module and then I find out, okay, I could just rewrite this algorithm in my C++ program.
Yeah.
So I just take the module as it is, but
Yeah.
then I just replace the function with the module.
It's this line. That's how you do it.
Yeah.
I mean, the function lookup is always done at runtime. And the lookup is, again, this is a table lookup. It will look for the name print in this _g table.
Cool.
So,
Then
yeah.
that answers the question.
Yeah, okay.
And then easily restore the original version.
Could I restore the original version? So this is, yeah. So the thing is, once you've lost track of that function, so like let's say like in your C++ program, you nowhere have the original Lua function in scope through a header or something, and you overwrote it in Lua and you did not save a copy, it's very hard to get it back. This means that this is actually a cool feature for sandboxing, because if you don't want your like if you're writing an application and you want to enable clients to write plugins, and you don't want them to have access to certain functionality, You just don't assign those functions, and then they basically don't have any means to get them back from within the Lua code. So yeah, it's a feature. Question in the back.
There was this example where I think C++ 17 destructuring was used
Yeah.
to destructure the arguments. Yes,
The ABC here. Yeah.
that's it. And because probably this the function call probably returns some generic object. Do you have any idea how like the author solved this issue? So we know how much arguments like the function.
Yeah. So yeah. So the question is basically what the type of the A, B, and C is going to be, right? That's what it boils down to.
Yes, right.
So
Because,
yeah. So what I'm not 100% sure, but I think what will happen is that Sol will return proxy objects here. So A, B, and C will have the type of generic proxy objects, and then when you try to use them in a context where a certain type is required, like for example you want to assign them to an int, then and only then it would attempt to perform the actual type conversion. And if the value that is stored in there is actually not convertible, then you would get a runtime error, but actually like Sol tries pretty hard to convert it, so you're much more likely to get a nonsensical value in that case. Okay, with that, our time is up. Please, if you have any more questions, come talk to me. But thank you very much for your attention. Good night.